Okay, so we're back again, and we are going to talk about the last bit of notes for this particular unit, and then we should be able to wrap everything up, and you can start working on your review. Okay, so the first thing that we need to talk about is something called Dalton's law of partial pressure. This applies to a mixture of gases. To be very honest, the vast majority of gases that we deal with in chemistry lab are some type of mixture of the gases that we're attempting to work with. So like the atmosphere has got like nitrogen in it, it's got argon in it, it's got carbon dioxide in it, and oxygen in it. So when we talk about the atmospheric pressure, it's really the sum or the total of all of the gases that happen to be floating around at that particular place at that particular time. Partial pressure is the pressure of that one component of the mixture of gases if it were all by itself. So basically what I'm saying is that the more gases that I add to a container, each gas has its own individual pressure that it applies to the container to have some type of summative pressure. So I'm going to kind of show you how that works in an example here. In a mixture of gases, nitrogen exerts a pressure of 0.421 atm. Oxygen exerts a pressure of 0.211 atm, and argon exerts a pressure of 0.110 atm. And so if we're asking what the entire pressure is exerted by the mixture, we would go to the partial pressure law, which says P total is equal to pressure of gas A plus pressure of gas B plus pressure of gas C. And then specifically, we're going to be talking about pressure of nitrogen, and we're going to be talking about pressure of oxygen, and we're going to be talking about pressure of argon. So when we want to find the total, we would take the pressure of nitrogen, which was measured to be 0.421 atm, plus the pressure of oxygen, which was measured to be 0.211 atm, plus the pressure of argon, which was measured to be 0.110 atm. And so we simply just add them up, and you get a value for the total pressure of the system to be 0.742 atm. So when we talk about Dalton's law of partial pressure, that's all that this is really asking us. And the reason why this is important for us is because when we go to try to collect gas over water, what ends up happening is that the gas that is attempting to be collected over water is not pure. So if I'm doing a reaction and I'm producing a gas like hydrogen, for example, and I'm collecting that hydrogen gas in a balloon or some other collection device, the hydrogen gas is not just hydrogen. There's a small amount of water vapor trapped inside there, in large part because water is constantly evaporating and turning into a vapor. So when we are asked to work with or identify the pressure of the gas that we're creating, or that we're creating or collecting, in this case hydrogen, there is a table that we can consult that will allow us to decide what the actual pressure of hydrogen is based on the water vapor pressure at a very specific temperature. So how that works is we use this new formula, which is a variation of Dalton's law of partial pressure. The total pressure of the gases is equal to the pressure of the gas that we're collecting, hydrogen, plus the pressure of the water vapor. So in the case of this one, P total is equal to the pressure, if water vapor exerts a 15.2 millimeter of mercury pressure, and the total pressure is 749 millimeters of mercury, what is the pressure exerted by the hydrogen, which isn't too hard for us to figure out because it ends up being a pretty simple math problem. So pH2 plus pH2O is equal to the total. Well, I'm telling you that the total is 749 millimeters of mercury. We're trying to solve for pH2, and we know that the water vapor pressure is 15.2 millimeters of mercury. So we do some very simple subtraction, and we get a value of let's see, 749 minus 15.2, and we get something like 733.8 8 millimeters of mercury, and then because 749 has no decimal places and so 15.2 has 1, it ends up being something like 734 millimeters of mercury with sig figs and all that fun stuff. So that's not too bad. We now need to talk about Avogadro. Avogadro actually came up with his relationship that we've been using since we talked about stoichiometry and moles a long time ago by working with gases. And so what he was able to determine was that he basically said is that if you have equal volumes of gases at the same temperature, you should have the same number of particles of that gas. He didn't know what a mole was at that point in time because that was about a bajillion years ago, but he did know or was able to identify that the number of particles of gas in 1 liter at 30 degrees Celsius was equal to the same number of particles of a different gas in 1 liter at 30 degrees Celsius. So there's some formula that goes along with that that says that N1, which is the initial volume of moles, or initial moles, over V1, which is the initial volume of a gas, is directly proportional to the number of particles of a different gas or the same gas at a different volume or a different number of moles. So long story short, 2 equal volumes of gases at the same pressure and temperature contain the same number of particles, which is really what's important to understand. So if we were to apply Avogadro's law, we would, because of the information that we know, equal volumes of gas at the same temperature and pressure contain the same number of particles, the mole ratio in a chemical equation can be used to compare volumes of gases. So if I'm using the equation 2H2 plus O2 makes 2H2O, essentially the production of water, I can determine the volume of hydrogen needed to react completely with 6.5 liters of oxygen if the reaction is done at 15 degrees Celsius and 0.994 atm. This is really important because as long as both parts of the equation are at these conditions, then we can use the simple formula above. So I'm going to say that N1 V1 equals N2 V2. I'm going to set them equal to each other, but I'm going to replace them with NH2 over the volume of H2 is equal to NO2 and the volume of O2. So a couple of things that I know for sure. If I'm told that the volume of oxygen is 6.5, I have to assume that the volume of hydrogen is going to be some relative value according to that. So in this case, I know a couple of things for sure from the balanced chemical equation. I know that the volume of O2, or I'm sorry, the number of moles of O2 is 1, and I know that the number of moles of H2 is 2. So there's a relationship there. So I'm going to go plug in what I know. 2 moles of H2, I'm looking for the number of volume, or the volume of H2, and the moles of hydrogen, or oxygen rather, in this particular equation is 1 mole of O2, and we have 6.5 liters of oxygen. So now we're going to do some cross multiplying, and when all is said and done, we will determine that the volume of H2 in this case should be roughly, well, 2 times 6.5 divided by 1 is 13 liters of H2. So that's not too bad, and we don't use this formula very often, but you just should be aware. Now, the next couple of things are simply definitions that you have to be responsible for understanding. The first one is effusion. Effusion is the ability of a gas to move out of a container through a pin-sized opening. Think about like when you have a balloon and you keep the opening of the balloon very, very tight, and you squeeze and you kind of separate that balloon. It makes that loud screeching noise. That's an example of effusion. The gas is rushing out of the container through that very tiny opening. Diffusion is the ability of a gas to move from an area of high concentration to a low concentration. An example of that would be when you come in the house. I guess when you come in the house and you smell that your mom or dad are making something really, really delicious, when you come in, you get hit in the face with that smell. But if you go upstairs, like say to your bedroom, and the door's been open all day, you might not smell it quite as much because the gas particles haven't quite gotten there yet. Now, if they cooked something awful smelling like fish, that smell might eventually make it up to your bedroom, and that would be an example of diffusion. So the rates of effusion and diffusion are really, really determined by the kinetic energy or temperature that the particle has. So particles with larger molar mass tend to move slower than particles with smaller molar mass. This is pretty simple. The bigger the particle, molar mass, the slower the object is going to move. So H2 is going to move faster than something like Cl2 just because of the mass. Also, at higher temperatures, particles tend to have more kinetic energy, so they diffuse and effuse faster. You get those gas particles moving faster, or you give them more temperature, they move faster, and as a result of that, they will go through the process of diffusion or effusion faster. The idea of the kinetic molecular theory, something we're going to spend a lot of time talking about in AP Chem next year, makes some assumptions. Gas particles are not attracted to one another, which is why they fill the container that they're put into. The volume of the gas particles can be ignored, so that the volume of the gas is equal to the volume of the container. Again, that goes back to the fact that they're not attracted to one another, and no energy is lost when gas particles collide with each other and with container walls, so the energy of the system depends only on the temperature of the system. These are called elastic collisions. It's like when you are playing the game of pool and you hit a ball really, really hard, and it transfers all of its energy, or the cue ball really, really hard, and it transfers all of its energy to another ball. The cue ball stops, the other ball keeps going. That's a transfer of energy. That shows that energy is lost. However, when we're talking about gases, when those two balls would collide with one another, both of them would have the same energy as when they left. And gases can behave ideally when temperatures are relatively high and when pressures are relatively low. How high and how low? We're just going to say really high and really low. It doesn't. There's no real great number associated with it. But what that tells us is that gases aren't ideal. The vast majority of gases that you're going to ever deal with are going to be real gases under the conditions that we measure outside in the world. But we crank the temperature up to like 1,000 degrees Celsius, and we make the pressure be like something like 0.1 atm, then gases will tend to follow the things that we just talked about in terms of conditions where the ideal gas law applies. When temperatures are very low and pressures are very high, so the opposite of this, the substances that are the gases tend to start behaving like a liquid or a solid. So we remember when we talked about those different phase change diagrams, like the triple point diagram. That's where we talked about the triple point, where things were a solid, liquid, or a gas. That's the situation that we're talking about here. Okay, so that pretty much sums up everything that you need to know about the Unit 10, and if you have any questions, we can talk about it the next time I see you. Good luck.